And so now we notice that we're given the function f, and this function is a line. Looks like the slope is always the same, and so its derivative should be constant. Floor is open for questions. Match the function on the right with its derivative. We'll burn through this homework together if you're feeling it. If you want to practice these, you can go to the study plan, chapter 3, section 2, problem number 49. The following figure gives the graph of the derivative of a continuous function that passes through the origin. Again, f, f prime, f double prime. Looks like they've given us the derivative. This is f prime. Which one is the function graph with this, the antiderivative, right? So you're looking for the original function. Now it's here that we have to remember some rules. Now I'm going to write these down the first few times until you're just like, Winger, stop writing this. I know, right? When f prime is positive, f needs to be moving up. F prime negative, f needs to be moving down. So what does that mean in terms of the graph? That means that when the graph is above the x-axis, let's write it. I'm all about being direct. When f prime is above the x-axis, f needs to be going up. And when f prime is below the x-axis, the original function needs to be going down. And family of mine, almost that on its own should help us burn through this thing today. All right, so now above f, this is again f prime. It's above the x-axis, so the blue graph better be going up the whole time. What is this doing? Oh, again, the pink graph is above the x-axis. That means the blue graph should be going up. Are there other choices other than C? No, that's it. Let's check everything else, right? When this is above the x-axis, the blue graph is increasing. When the pink graph hits the axis, that means that the blue graph should be flat. I'm convinced. Let's just keep going for just a second. When the blue graph when the pink graph is negative, the blue graph starts to go down, and when the pink graph starts to be positive again, the blue graph starts to increase. I think we're rolling with 14 of these. Beat me to the end. We're going to translate. Sketch a function that is continuous, no breaks or no jumps, and has the following properties. By the way, this is on the final, right? So and this is not my choice, right? I went to the meeting with the other calculus teachers, and I sat there as they said, oh, we should give them this and this and this and this, right? And this is one of them. We're going to give you one with these options, and you have to pick the right graph. Now, it's not exactly this one, but I'll pick something from this assignment and then put it on the final, okay? So make sure we got this down cold, and this is the time to ask questions, whether I'm recording or not. It can be edited. All right. Sketch a function that's continuous, so no breaks or jumps, and has the following properties. Use a number line to summarize information about the function. All right, it's decreasing. I should use a thinner marker. Let me use a thinner marker here. Because I've zoomed in, the marker looks thicker than what I want it to. So it's decreasing before 4. Before -4. It then starts increasing. We're just translating from -4 to 1, and then it starts decreasing again after 1. right? And by problem number 14, we'll have this cold. Which one is that? Decreasing before -4, decreasing before -4. All right. It starts increasing from -4 to 1, and then starts decreasing after 1. Questions? They made a function between increasing, decreasing, and red and blue. When the function is increasing, in other words, when the derivative is positive, they're going to make some claims about, oh, they're also using whether the function's positive or not. Oh, that's interesting. So what did we say before? So it looks like it's decreasing, then increasing, and then decreasing. I like this one. Right? Decreasing, increasing, and then decreasing again. Right? So these are comments about the function, these are comments about the derivative. Sketch a function that's not constant, that is continuous, no jumps, no breaks, and has the following properties. Use a number line to summarize information about the function. Wow, it's flat in a ton of places, right? So it's flat. So I really hate this statement because they are just being straight up lazy. And it's because they want to say stuff about the function and stuff about the derivative all in the same line, and I can't stand that. It feels like they're purposely trying to be just assholes here. Okay, so f of -3 is 0, f of 1 is 0, so it's saying the function goes through the point -3, 0, and it goes through 1, 0. So it hits the axis at those points, right? So it hits the axis here. That's too thick, I'm sorry. So it hits the axis there. So we can get rid of some of these now, right? So this is by 2. Okay, so -3. This is not -3, right? You're going by 2's. I don't think that's -3 here. All right. I'm not convinced. Is any one of these -3? -3. Okay, well, there's one. There's one. Okay, so it could be that one. All right, so good. It's either. It's definitely not this one. It hits the axis at -3, and that is not -3. Okay, good. It's flat at these 3 places, right? So when you write, so this alone, let's use a different color. So this alone, this one, this alone says it's flat. The derivative is 0 at -3, at -1, and 0. And of course, both C and D do that. Flat here, flat here, flat here, flat here, flat here, flat here. That doesn't help us. All right. Oh, and then the function is always above the x-axis, or it might hit a couple of times. That's it. The function's always, so we can translate that one. Always, always above or on the x-axis. Okay, so what is this function doing? This function is decreasing, so it should be red, blue, red, blue, red, blue. I'm failing this one. What's the difference between A and, oh, is it actually, you actually got to pay attention to where this is happening. It looks like it's at 3, right? Ugh, 0, that's 0? 0, 1, 2, 3. All right, so you actually have to be paying attention here, and that's 1. All right, so that's why it's B. So you just can't do it by inspection like the previous one. Decreasing, increasing, decreasing, increasing. Okay, keep rolling through your assignment as well. Sketch a function that changes from concave up to concave down as x increases. Concave up to concave down. So it needs to look like something like this. Wait, concave up, I'm tripping. Concave up, and then the concave down all of a sudden. This one's concave down the whole time. This one's concave down to start, concave down to start. Choose the phrase that best describes the behavior of the second derivative. Second derivative starts out concave up. The function starts out concave up, so that means the second derivative is positive and then turns to negative. Let's see if one of these says that. The second derivative changes from negative to positive. No, the second derivative changes from positive to negative as x increases. All conceptual, right? All right, we'll go back to our notes. Sketch, right? So we're just rolling with this, right? So we'll draw this again. All right, so we've got f prime negative, f double prime negative. I'm sorry, f prime here is positive. Right, this function is going up. F prime positive, f prime negative, f double prime negative, f prime positive, f double prime positive, f prime negative, f double prime positive. I need them both to be negative. I need to be going down and be facing downwards. Looks like it's this. And they're saying this is the case over the whole line, everywhere. The whole time. Sketch a graph of the function f that's continuous on a whole row line, no breaks, no jumps, and has the following properties. I need f, let's translate. F has got to be increasing and concave up before 2. So something straight up is happening. So increasing, concave up. Increasing, concave up. Increasing, second derivative. The first derivative is positive, concave up, again from the previous page. Okay, and then all of a sudden it keeps increasing, but then it turns concave down. Well, first of all, it can't be this one. It can't be that one. Honestly, I think again the only issue here is that this is happening at 2 instead of 1. Right, so it's happening at 2. Floor is open for questions there. Let's get a little wicked. Consider the graph of f and f double prime shown on the right on the same set of axes. Sketch the graph of a possible function f. The graph of f is not unique. Yeah, you could graph all sorts of things. But let's see here whether we can conclude what the green graph, so this is, they tell us that f prime is the blue graph and f double prime is the red graph. They're now going to give us 4 options with a green graph thrown on it. And the question is, can we find out which one is at least an option for the original function. Okay, so I need to use a color that's not one of these. Let's use orange. All right, so I got to keep track. The blue graph is f prime. The red graph is f double prime. All right. So usually what I tend to do is I use the blue graph to start eliminating. Again, whenever f prime is positive, the function needs to be going up. So that means above the x-axis, the function needs to be increasing. Above the x-axis, it doesn't look like it's increasing. Above the x-axis doesn't look like it's increasing. All right, so that actually looks reasonable. I'm worried about the here, right? So here, this thing's supposed to be flat. Now it might be, but I'm worried, right? So that at least is good. It crosses here. I don't know what's going on with the green graph here, but we'll keep moving on. So now the derivative is under. The derivative is under the x-axis. The function is the derivative is negative. So the green graph should be decreasing here, and it is not. So this was all discernible just from what the blue graph is doing, right? I mean, again, it is hard to just discern, right? So it's overkill to even have the second derivative. But I mean, you could, I suppose that we could have used that as well, but the blue graph tells us almost everything we need to know. And again, we can keep going forward, right? So the blue graph is negative here, and this whole time the blue graph is under the x-axis, the green graph is going down until at the very moment the blue graph starts to go above the x-axis, the green graph starts to increase. Great. The figure to the right shows the graph of a function. So here's the function, f. Match the function with its derivative and its second derivative. Great. All right. Now they won't put them on the same graph, so that's good. There's f. Now we're going to say some things about f. Now remember, we want the things we want to say about f is that it's increasing or decreasing. And then the things we want to say about f prime is that f prime is positive or negative, respectively. All right, so the things we'll notice about, we'll use a different color, about f is that it looks like it's increasing before 0 and that it's decreasing after 0. And so the derivative should be above the x-axis before 0 and then below the x-axis after 0, and then it should be on the axis here. Okay, so first of all, they've taken care of the fact that the derivative should be 0 at 0. So they all do that. Okay, and so before the y-axis, the function should be above the x-axis. That gets rid of this, and that gets rid of this. So this is a statement about f prime. The function is decreasing after 0, so its derivative should be under the x-axis after 0. So again, we looked at the function and then we started talking in these terms and then translated to these terms. Now we're going to say something about the second derivative. right? And so now when the function is concave, oh, let's make a separate table for the second derivative over here. All right, so then now we'll do this. So then now when f is concave up, the second derivative needs to be positive, and when it's concave down, the second derivative is negative. And family of mine, this one is always concave down. So the second derivative should be completely under the x-axis the whole time before we even look at it. Oh. The function is concave down the whole time, so its second derivative should be negative the whole time. The accompanying figure shows the graphs of f, f prime, and f double prime. Pure madness. Pure madness. Which curve is which? So we've got A, B, and C. Right? So we got some stuff going on here. So now we know what we need to be looking at. We need to be looking at some stuff here, right? So we got f, f prime, and f double prime. So we need some discerning facts, right? And so we know, I feel like a detective, right? So we know that when f prime hits the axis, f, because everything is smooth, this is only happening because everything is smooth, then f should be flat. And in this case, because everything's so humpy, this means that you're at the top or bottom of a hill. Floor is open for other people who do it different ways, but that's where I start. That I'm going to notice that when one of these functions crosses the axis, then that forces the other one to have a hump. And I already know that that means that one is f prime and one is f double prime. Now, it may be the case that I'm looking at f double prime and f prime, and so we got to break that down as well. But let's see if we can find that. The floor is open. I'll take any suggestions about which is which. We got A is blue. Why can they make B blue? A is blue, B is pink, C is green. All right, so let's see. So it looks like here when A crosses here, so when A is 0, so here's a place where both A and B are 0, and C is at a hump, okay? Now, when A gets positive, it looks like C starts increasing. When A gets positive, it looks like C starts increasing. And it looks like when A is negative, C is decreasing. And when A hits this bump, C is at a hump, right? It looks like that at least that the derivative of C is A. Looks like A is the derivative of C, okay? And maybe that B is the derivative of A. Let's check here. Can we see that? That B is the derivative of A? I don't believe that, right? So then let's check let's verify again that A is going to be the derivative of C. That looks like the case. So now the question is C saying something about B? Oh, it looks like it is. When C is 0, B has a hump. When C is 0, B has a hump. So now let's see if that always happens. Oh, here's another place. When C is 0, B has another hump. Let's just be clear. When C is positive, B starts increasing. It looks like the derivative of B is C. Looks like B is the original function. B is f. Looks like C is the derivative of B. And it looks like A is the derivative of C. Completely funky. Right? But it's just playing with all these rules. Have fun with the one you got. Right? So going through that analysis. But just checking where they cross and whether that makes a hump in another one, and then breaking that down as you move. Now I started all the way to the right. You can start on the left, right? But that's crucial, right? And so it's like these points tell you what's going on in a lot of ways. And they tried to make it as hard as possible. So great. All right, 11. Sketch the graph of a function f continuous on a, b such that f prime, and f double prime have the signs indicated in the following table. There are 8 different cases lettered A through H and 8 different graphs. Complete parts A through H. Which is the graph for case A? F is positive the whole time. Bam. Right, let's just verify all the other stuff. Right, but it says F has to be above the x-axis the whole time. This is the only one that's above the x-axis the whole time. But let's just verify the other stuff. F prime is negative. Yep, it's going down. And F double prime is positive, concave up. That one is A. B. B says that F is always under the axis. This one says that F prime is positive, which means F should be increasing. It should be going up. And here we are, right? That here we are with a function, with 2 functions that are both negative the whole time, and they're both increasing. And here's the impact of the second derivative, and that it will tell us how we're curving. B, F double prime is negative, concave down. C, negative, positive, positive. Function's negative the whole time. Is it going up or down? C, F prime is positive and it's concave up. Increasing, concave up. D, positive the whole time. They're being bad with their positive the whole time, decreasing, concave down. E. Whew. Positive. Oh, gotta go to the next page. I think this got cut off. Oh, I think my picture for it. So, but everything's positive, so it has to be above, increasing, concave up. Looks like that, right? So it looks like it's going to be this one. Whole thing's positive, increasing, and concave up. Looks like it's going to be that one. F. F was negative the whole time, minus, minus, plus. Minus, minus, plus. Function's always negative. Function's decreasing, concave up, minus, minus, plus. Almost there. G, minus, minus, minus. Negative the whole time, decreasing, concave down. Plus, plus, minus. Plus, always positive, increasing, concave down. Plus, plus, minus. Take any questions about any of those? Sketch the graph of a function that's continuous, no breaks, no jumps, on the whole real line, satisfies the following conditions. All right. Translator. Concave up before -4. Cave up before -4. Gotta thin this thing out. All right. Concave down between -4 and -1. Concave down on this interval, and then goes concave up on this interval, and then it's concave down after 1. So now the second derivative just tells us all this stuff. All right, so concave up before -4, 1, 2, 3, 1, 2, 3, 4. So it's concave up before. I'm not happy with that because this looks concave down right here. Concave up before -4. Okay. Okay, I think I'm liking that. Concave up before negative. Okay, good. Okay, the rest of them are good with that. Concave down from -4 to -1. -4 to -1. I'm liking that. -4 to -1. Uh-oh. I don't think this one's working because this one's supposed to be concave up from -1 to 1, and this doesn't look like it's concave up. Right, so I don't think it's this one either. So what was given away here? What was given away is because you went from concave down to concave up through -1, it meant that -1 needed to be this inflection point place, right? And that's not happening when you go from negative to positive through -1. That doesn't seem to be happening here or here, right? Really, right? We can check again. We can check some more. And it's concave down from 1 to infinity. Concave down from 1 to infinity. No, I don't like that one. Concave down. Oh, it's not this one either. This one came back into my life. Concave down from 1 to infinity. There's 1. That's supposed to be facing down. Okay, D. The 1122 for some reason in this one. Decreasing concave down before 22. Decreasing concave down before 22. And then decreasing concave up. They don't give you the full picture, but I know it's not the other ones. Right? Not concave down. Not concave down. Concave down, and then it stays concave down. 14. Use the graph of f prime and f double prime to find the critical points and inflection points of f, the intervals in which f is increasing and decreasing, and the intervals of concavity. Then graph f assuming f of 0 is 0. All right, here's some definitions. Critical points. We define inflection points. Critical points are where the derivative is 0. Inflection points are places where, we said this before, inflection points where the second derivative is 0 and the concavity changes through C. Did they tell you which is which? Oh, they've done a terrible job at which is which. I'm assuming, why couldn't they just put it here? I'm assuming that that's f prime and that the blue one is f double prime. All right, so they're critical numbers wherever the derivative is 0, and so that would be 1 and 3. By the way, let's notice that the function itself is nowhere to be found, and we're saying something about the function. All right, so I know there's going to be critical numbers there. The function's flat at 1 and 3 because the derivative is 0 at 1 and 3. Inflection points are places where the derivative is 0 and the function changes from, the second derivative changes from positive to negative. So it looks like there's an inflection point at 2, right? Because the second derivative is positive before 2 and then it's negative after 2. This function, even though we can't see it, is concave up before 2 and then concave down after 2. Where is f increasing and decreasing? F is increasing wherever the derivative is positive and is decreasing wherever the derivative is negative. The function is increasing wherever the derivative is above the x-axis. That's from 1 to 3. The function is increasing on the interval 1 to 3. Interval notation. The function is decreasing wherever the function is under the x-axis. That looks like, let's use a different color. 0 to 1, 3 to 4, wherever the derivative is negative. 0 to 1, comma, 3 to 4. Find the intervals of concavity. F is concave up wherever the second derivative is positive. F is concave up wherever the second derivative is above the x-axis. Concave up here, 0 to 2, concave down 2 to 4. All of these intervals are open. Which one's F? Oh my goodness, this leads into the next section so perfectly, family of mine. Which one is f? So I need a function that is doing what? That it's flat at 1 and 3. I would be shocked if this thing actually has some bad, look here, like it can't be C and D, right? Look how nice the derivatives are. Right? These are ridiculous, right? Because these don't even have derivatives at 2, right? We'll see. But I mean, we've already said that you can't have any sharp points if you want 2 derivatives, right? So those are out automatically. So it has to be something nice, right? So we'll come back and see. But as far as we can see, the derivatives look nice and smooth. There should be no sharp points anywhere here. All right. So that gets rid of those. So now I need a function that starts off, is it increasing or decreasing? Ooh, it starts off decreasing. It decreases from 0 to 1 and from 3 to 4. It's got to be this one. Bam. Excellent. Great. I'll stop recording there.